Our last talk of the session is from Vlad Sivak on quantum error correction beyond break even. Take it away.
Thanks. So I'd like to start also by thanking the organizers for bringing us all together here. Very enjoyable conference. My name is Vlad. I work at Google, but today we'll be talking about this experiment on the error correction of a grid code that was done when I was at Yale University in the group of Michel Decoherence. So I want to thank all these amazing scientists for their contributions to this work, and also for just making Yale a very nice and creative place and acknowledge our funding sources for our monies. So probably many of you have seen this plot many times. It shows the progress in the quality of superconducting qubits over almost 2 decades. And one particular aspect of the quality, which is the lifetime, coherence time. And there's many orders of magnitude in this plot, which is amazing. And there are all kinds of qubits, quantroniums, fluxoniums, transmons, 2D circuits, 3D, all kinds of things. And something that they all have in common is that they are based on the energy levels of a static superconducting circuit. And so in this sense, we can call them passive qubits. And hopefully this progress will continue, but arguably it has slowed down a little bit in the recent years. And there is an alternative route that can take us orders of magnitude up in the direction, and it's based on quantum error correction. So we will call such qubits active because they require some intervention on our part, also just by contrast with the passive. And so the goal of our experiment is to show that this is really a viable route. And the way I like to think about it is that we need to show that by putting together these imperfect quantum components and doing imperfect operations on them, we can create a qubit that's more coherent than everything that we started from. So let's review sort of the progress of the field along these lines. So it's a very similar plot to what we've just seen. Vertical axis here is a slightly generalized notion of the lifetime. So it think about it as a time scale over which the qubit can maintain an arbitrary state. So it doesn't give any preference to any particular basis, averages over all states in the blocks here. And so there are all these different experiments on error correction. And for each experiment, there are 2 points. One point shows the lifetime of the best passive qubit that can be created in that system. And another point shows the lifetime of actively error-corrected logical qubit. And the arrow goes from the best passive to active. And so you see that in most of these error correction experiments, doing error correction, just because of all of the overhead that it requires, hurts the coherence of the qubit. But there are some good news. So already in 2016, there was an experiment on the CAT code from Rob's lab that has demonstrated reaching this break-even point for the first time, where these 2 lifetimes just equalize. And in fact, they were able to go 10% above break-even. And then the focus of today's talk is this result with the GKP code where we showed that we can go a factor of 2.3 beyond break-even. And also at the same time, with our work, there was a result from China that uses binomial code. So that's sort of an overview of the main results. And now let's go into the details of how we did that. So to create a qubit, we need 2 states, 0 and 1. So in principle, any physical system with a state space larger or equal to 2 can host a qubit. And in our case, the system is an oscillator. So this code, we've heard a lot about it yesterday. It was proposed by Gottesman-Kitaev-Preskill, so we often call it GKP code. These are the wave functions, so the code words in position representation. So they look like these grids of delta functions that have non-overlapping support. And because of this sort of large distance between them, these states have nice error correcting properties. And notice that they are periodic. And so they extend infinitely far, which is, of course, impossible. So in reality, we have this envelope which is superimposed on top of this grid. And all of these peaks are finitely squeezed. And these states were already created in experiments before. So for the first time, they were prepared in a traptine system, where the role of this oscillator is taken by a mechanical motion of the traptine. Error correction of the autonomous error correction of these states was also shown in traptine, and we'll have a talk later in this workshop about this result. And in superconducting circuits, the role of an oscillator is taken by this electromagnetic mode inside of a superconducting cavity. So I want to give special credit to this experiment here that basically made this breakthrough of realizing how to actually practically prepare these states in the lab and do quantum control on them. And the work that I will be talking about is largely based on these results. And also, there are some good news from Nord-Quantique that they presented at the March meeting, and I believe they will also be talking about this later in the workshop. So this is how they look like. This is experimental data, a Wigner function of logical zero state and different superposition states. Wigner function, in case you don't know what it is, you can roughly think about it as a ability distribution. So this is like a position x and like momentum. And so these are very interesting states because the particle can only occupy some small pockets in phase space and cannot be in these big white spaces where Wigner function is zero. So we prepared them in the system. It's a superconducting cavity. It has a standing mode here. And most of the electromagnetic field lives in vacuum. So it has relatively good T1s, 600 microseconds. No, Serge is somewhere here, probably smiling that I call this good. We'll hear later in the workshop about his results, like many milliseconds. But anyway, so we can prepare this mode in different quantum states. And if we want to embed a qubit into it, there is also many ways of doing that. And the simplest way is by using these lowest two energy levels. And we call this a Fock qubit because these are Fock states. And to control this oscillator, we couple it to this nonlinear element, which is this transmon circuit. It's also a relatively good transmon with T1 of 280 microseconds. It was made with this new fab technique based on tantalum that was recently developed in Princeton and then re-implemented in Rob's lab. And we can also create a qubit in a passive qubit in the transmon using these two energy levels. But just from perspective of lifetimes, this qubit is much worse than that one. And in fact, this is pretty much the best passive qubit that we can make here, because if you go to any higher energy levels in this circuit, there will be this bosonic enhancement of the emission rate of photons. And so the lifetime of any of these alternative qubit encodings will be lower. But the advantage that they give us is that they can allow us to do error correction. And so, like I said, in our case, it's going to be this GKT code. So now I'm going to describe the actual error correction process. And I want to start with an example of a repetition code, just because it's easier to explain. And I want to focus on this one aspect of how we can view error correction process as an artificial dissipation. So this is the repetition code of 3 qubits. This is the logical 0 state, logical 1. And together they form a code subspace of the full state space of this system. And these guys are all possible error subspaces that are generated from the code space by applying single qubit bit flip errors, which are the errors that this code is designed to correct. For example, this subspace is obtained by applying bit flip on the first qubit. And so this is the image of logical 0, this image of logical 1. They're orthogonal to each other, and they're orthogonal to everything else. And that orthogonality condition is the nil Laflamme condition, which is very important for error correction. So now, how do we do error correction? Well, the standard approach, which is called the stabilizer formalism, tells us that we need to go and measure these operators. They are called stabilizers. In this case, they are parities of the first two bits, the last two bits, the measurement outcomes give us this error syndrome. So in this example, it's 1, 1. Then we can look at it and decode it. And that means that we will infer in what subspace the state currently sits. So here we will infer it in C2. And then we can apply a recovery operation, which will correct this error and bring the state back to the code space. And together, all of these 4 steps implement this Krauss channel of rank 4. So there are 4 Krauss operators because they correspond to 4 different syndromes that we can get in this circuit. And so these are these Krauss operators. So the first one is just a projector into the code space. It corresponds to the syndrome, which tells us there is no error, so we don't need to apply any recoveries. So it's also kind of represented with this arrow. And you see that it looks like this tiny identity matrix inside of the block that corresponds to the code space. And then this other Krauss operator, it corresponds to the case when we found an error in this subspace C1, and then we corrected and it transfers the state to C0. So it looks like this transition matrix. And importantly, when this transition happens, it isomorphically maps the basis of this error space to the basis of the code space. It's basically defined by these things. And all these other matrices also look like transition matrices. And so by looking at these arrows, each arrow, each color corresponds to the Krauss operator. You can already see how this looks like dissipation. And in this case, this is the most efficient dissipation from the point of view of entropy removal from the system, because it corrects any of these 3 errors in a single application of this channel. But it's not the only way to do error correction. And so here is an alternative approach. It's just a different kind of dissipation. So this one has only 2 Krauss operators, so it's a channel of rank 2. The first one is the same as before. And the second one, it transfers the state between these neighboring subspaces. So it goes from C3 to C2, C2 to C1, C1 to C0. So basically all of these 3 red arrows are happening at the same time, which also is kind of represented with this off-diagonal matrix. And this approach can correct all of the same errors as the previous one. The difference is that it can't do that in a single application of the channel. So for example, if the error throws you into this subspace, it will take 3 hops to completely recover from it. And so in this sense, it's slower, and it makes sense to use it if errors have some kind of hierarchy, meaning that like, this one is much less likely to happen than that one. And repetition code doesn't have that a priori, but we'll see later that GKP code has that. And we call this trickle down because that's how it looks. And the reason I'm showing you this is because the QEC process that we realize for the grid code is much closer to this kind of dissipation than to that kind of dissipation. This is the circuit that we run to do error correction. I'm only going to explain it at the high level just because there isn't enough time. So this is some big unitary part that entangles the oscillator and the ancilla and maps this error information onto ancilla. We represent it as a parametrized circuit with multiple layers. All these layers, they have the same structure, but they have different parameter values. So each layer has a rotation on the ancilla qubit and this entangling gate, which is called echoed conditional displacement. And then after this unitary part, there is a measurement. And the outcome of this measurement is processed in a real time on the FPGA controller. So think about like a classical program that runs on this controller concurrently with this quantum circuit that runs on the quantum hardware. And they constantly talk to each other through measurements and feedback. Feedback here involves resetting the ancilla to the ground state and also implementing this virtual rotation gate on the oscillator, whose angle also depends on the measurement. And then there are 2 similar looking blocks in which we call cycles. And the full circuit realizes one full QEC cycle, and it takes about 10 microseconds. And I would just want to quickly outline that there is a lot of technologies that were developed over the past few years that basically went into enabling kind of running circuits like this. But for now, what's important for us is that the circuit has two measurements, this and that, and they are binary valued. So there are four possible combinations of these measurements, and that means that this circuit implements a channel of rank 4. So there are 4 Krauss operators, and we can label them using measurement outcomes from this circuit. So what are these Krauss operators? Well, so this is how they look. So you should compare this to that simple example of the repetition code. So the first Krauss operator looks diagonal in these airspaces. So it doesn't actually transfer the state between different airspaces. It's also shown with these kind of arrows. And then within each airspace, it doesn't look like an identity matrix. It looks like this off-diagonal matrix. That's because the circuit applies deterministic Pauli operation in addition to doing error correction. And then these other Krauss operators, they have this block structure. And this block structure is actually what allows us to arrange the airspaces in this way. So this block here corresponds to that airspace. This block here corresponds to these two airspaces and so on. And notice that this thing is empty while that is filled. And so that means that this Krauss operator transfers the population from these two airspaces down to the code space. And then similarly, because this block is empty and this is filled, there is a flow like this here. Yeah, so there is more. I'm just truncating it. So what are these airspaces? Well, the thing at the bottom is the code space. So this is a Wigner function that represents the code space. It's a Wigner function of a fully mixed state inside the code space. So equal mixture of 0 and 1. And these are error spaces. So they look kind of funny. They look like you take these little vacuum states and replace them with little POC1 states. If you look inside this black circle, you will see the difference between them, that the red is biased kind of away from the center here, towards the center there. And we can ask, so what errors generate these subspaces out of the code space? And it turns out that this is approximately photon loss and photon gain errors. And so now the way you should think about the whole QEC process is that different errors just heat up the system. They excite it out of the code space into these higher error spaces. And then error correction cools the system, so it dissipates you back to the code space. So now that we kind of understand how error correction works, we can look at the results of a few different experiments with the system. So here we're just watching how logical decoherence happens over time. So we prepare logical 0 or logical 1 state, turn on this error correction process, run it for some number of cycles. So here it's 0 cycles, and this goes up to 800 cycles, which is about 4 milliseconds. And then we stop and we just take a snapshot of the Wigner function. And so this is Wigner functions right after state preparation. So you see that they are sort of distorted. They don't look very nice. And then error correction quickly fixes up these distortions. And then after 100 cycles, the state is already nicer. And then as time goes on, this pattern that allows us to identify which of the two states we're looking at just gradually decays. And eventually these states look almost the same. So that's exactly the process of logical decoherence. Then the same thing is shown at the bottom, where we just look at the probability distribution of the position of an oscillator, which is obtained by integrating the Wigner function. So at time 0, we have these very nicely separated peaks that I showed you the cartoon of this before, but now this is like a real measurement of the wave function. And you see that as time goes on, this blue state, which is 0, starts acquiring these peaks in the locations of the opposite states. And then they keep growing until these states mix completely. And so the logical channel that describes this decoherence is actually a Pauli channel. It just mixes these two states together. So now what we can do with this data is look at each Wigner and reconstruct the density matrix, and then look at its spectrum. So the spectrum of the density matrix tells us which pure states are mixed inside of this density matrix with what probabilities. And so we can look at, as a function of time, we can look at these eigenvalues here. So if we had a pure state, there would be only one eigenvalue equal to 1. So that would be like 1 point on the top. The fact that we have multiple means that these are impure states. And you can maybe see the pattern already, but I'll just add these lines here. So this is exactly the logical decoherence happening in these different subspaces of our system. And we can look at the projector onto this pair of eigenvectors and that pair of eigenvectors to identify what subspaces are we looking at. So that these projectors look like that. And just to remind you, this is something I showed on the previous slide, that in theory, this is what we kind of expect. So the first subspace, we can identify that that's the code space, which kind of makes sense. And this other one looks like the subspace that corresponds to a photon gain error. So another thing we can do is calculate the sum of these eigenvalues within each pair, and that will be a constant line. And this constant gives us the probability of occupying each of these subspaces in this dynamical equilibrium, where errors excite you out of the code space and then error correction takes you back. And for the code space, this probability is about 82%. So I'm gonna skip this. So this is another measurement. This shows these measurement records that we actually received from the QEC circuit. So time runs that way, goes from 0 to 1,000 cycles. And green means the G outcome, yellow means E outcome, and red means leakage. The fact that most of the plot is green is very good because that means that errors are rare. And then if we unpack this, whenever we see an outcome GG, it means that no error was corrected in that particular cycle. So I showed you previously the Krauss operator that corresponds to this outcome, and it's most likely to happen if the state is in the code space already. Then whenever we see these speckles of yellow, that means that in that cycle, some error was at least partially corrected. This interesting pattern here means that there was a big error here that took many cycles to correct. Then there is these isolated red dots, which is leakage to the F state of the transmon. So our circuit actually can reset this F state back to the ground state using feedback. But if this leakage happens to a state higher than F, then we don't address that. And then the transmon will be stuck in that state for a while until it just randomly decides to fall back to a computation manifold. So what we can do with this data is average across all these different shots and look at the probabilities of different outcomes as a function of time. So you see that they remain relatively flat. I want to bring your attention to this axis break. So this measurement actually runs to 100,000 cycles, which is about half a second of time. And during this whole time, this still remains very stable. So that's a good signature that this process is really stationary, that our envelope of this GKP code doesn't keep expanding. It also doesn't shrink to vacuum, really remains well stabilized. And so this is just the average, but we can do other kind of statistical analysis with these things, with these strings of measurement outcomes, and extract other characteristics of this dynamical process. For example, we can extract the probability of occupying the code space, which is about 81%. And this is a completely independent measurement. And I showed you how we extract this number before from Wigner function. They agree very well. We can also extract this rate of heating out of the code space, which is about 13% per cycle. Okay, so this is my last one. So previously, I just showed you sort of different bits of data that showing that we kind of understand what's going on in this system. But really, our goal was to show that we can take together these imperfect quantum components, do operations on them, and then create a qubit that's more coherent than all these components. And so this is the data set that kind of shows that. So first I want to introduce this notion of lifetime. So we derive it from this metric called average gate fidelity. In this metric, you take a quantum state, you pass it through the channel, and then you compute the overlap with the initial state. So it's just a state transfer fidelity, and then it's averaged over all possible states on the Bloch sphere. And that's why it's called average. So if this channel is identity, then this is 1. And if this is some error channel that acts over time, then this fidelity will decay in time. And this decay is not going to be a simple function. It's not going to be a single exponential, for example. But if we want to kind of define some single time scale, then we can expand it to first order, define this rate gamma that characterizes how this Bloch sphere decays overall from all directions. So it doesn't give any preference to any axis. Fortunately, as Mike Nielsen showed here, we don't need to sample all possible states on the Bloch sphere to measure this. And it's sufficient to just prepare 6 cardinal points that correspond to Pauli eigenstates, and then measure their decay rates, and that would give us this gamma. And so this measurement, that's what's shown here on the left, for these 2 different passive qubits that we can create. First one that's based on the lowest 2 energy levels of the transmit circuit. This is lowest 2 energy levels of this cavity mode. And this is the active qubit. So empty circles show how it decays when we don't do error correction. And you see that it actually dies off even faster than transmit. And then the solid circles show decay with error correction. And you see that it really lives longer than all of these other qubits. And then if we want to kind of put a single number and do a comparison among them, that's what's shown there. And that's how we know that we are a factor of 2.3 beyond breakeven. So, okay, so I'm gonna stop here. If you're interested, I'm here and we can ask questions. Also, please check out our paper. And there is an enormous supplement with a lot of videos.
So you have this trickle down versus instant recovery.
Oh, yeah.
And you have these 2 processes you mentioned in the beginning where you contrast them, trickle down versus instant, right? And yeah, conventionally people like instant. But how did you get to use trickle down? Is that what basically the reinforcement learner spit out? Or is that something you gave it as an ansatz? How did you come up against it?
Yes, so this is the ansatz from this circuit that I didn't explain because there was. So this circuit was proposed in this paper, and then also, I guess, independently by the science people. So if you find crossovers corresponding to that circuit, so there is some initialization of parameters here that I'm not showing. Like, for example, the amplitude of this displacement is like 2 square root pi and so on. So if you do that analysis with this circuit, that's how you extract those crossovers.
But did those papers, were they aware that this has turned out to be a trickle down when you look at it with photon loss, or did you do that analysis? Because they had a bunch
Yeah. I think, I don't know if you guys knew about this, but we didn't know about this, and we kind of discovered this after experiment.
Okay, so it's an ansatz. It's not like the reinforcement learner told you.
Yeah,
trickle
no.
down.
Reinforcement learning. Yeah, I think I also didn't mention that we trained the parameters of this circuit in experiment using reinforcement learning. And mostly what it does is it compensates for all miscalibrations that we have here. And it finds the parameters that we don't know how to choose. For example, when you do this gate, the way we implement it in circuits is using these large displacements in phase space. And in principle, you can displace very far, get very fast gates, but then you enhance different nonlinear processes. And where the middle ground is, or where the best fidelity for the gate is, we don't know. And so this is something that reinforcement learning chooses from data. And there is a few other things like
that. Very nice talk. So once these parameters are, optimized and determined, do you ever have to like recalibrate the parameters, or does it kind of hold up and works out.
Yeah, thank you. I have a slide for that. So this is a measurement where we just look at the different lifetimes in the system. So this is T1, T2 of the transmon, T1, T2 of the cavity, and this is lifetimes of different polyeigenstate of the GDP code. So we just trained here in the beginning, and then we fixed these parameters, and then this is 1 week. And so there is this kind of time scale over which the performance just degrades overall. And that might be because of these miscalibrations. So we do this kind of training every once in a while on like a week time scale. Then there are these kind of things as well, which are because of the spurious systems that come in resonance with our transmon.
One more question. So naively, I would think that the logical Y is the longest logical operator, so that Ty should be pretty long, but then it seems like the Y lifetime is the worst. Why is that the case?
Why lifetime is the worst because the way we do these conditional displacements, we do them along the X and along the Z operator. So there is a mechanism of how we induce logical X and Z errors, which affect the Y state. And that's why it lives the worst.
Hi, thank you for the talk. About the reinforcement learning, so you said that, for example, you have this optimization of how far you go in phase space. Do you get in return like any insight of, for example, can you do process identification of what are the higher order processes that are limiting the distance you go in phase space?
Yeah, we didn't look too deep into this, but one interesting observation is that it converges, like we did multiple trainings over like the year that it took to do this experiment. And reinforcement learning converges consistently to 2 different values of this large displacement. And the reason is that there is sometimes a TLS that appears close by in spectrum, and sometimes reinforcement learning chooses to not kind of push far in the phase space in order to not stuck shift into resonance with this TLS. But when it's not there, it can go all the way. So that's one sort of correlation that we noticed in this training. But otherwise, it's pretty difficult to analyze why it chooses what it chooses.
So in the plot where you showed the eigenvalues of the density matrix, I suppose there are many more as well, which are not showing, and those correspond to these other C3, C4, etc. So how much precision do we have and how far can we go?
I think our sort of noise floor for this measurement is about 1%. And so if we don't see anything above that, that means that there may be populated, but with just much lower probability.
Does that mean that the trickle-down is really only at the level of
No, it just means that it's very efficient in confining you to these 2 subspaces. But in principle, you can go up and back down. It's sort of like a thermal equilibrium for the transmon, let's say. If there is a heating rate, then you would be in equilibrium. There will be, mostly you would be in the ground state with some small probability of excited state, even smaller probability in the F state. So that's the same thing here.